All right, we can get started now, maybe. All right, so homework 4 will be released tonight. It's due a week from today. We'll have office hours today. That's the normal office hour time. We'll be directly after class. So we're aiming to release the exam 1 scores on Wednesday. They take a lot longer to grade sometimes than other years, so we're working through it. So where are we in the class? Let's see, so now we're working on interrupts and interrupt preemption, so we got a little bit ahead of our schedule. And this week you're doing or finishing up the interrupts lab. Next week we're going to start projects, right? So, or start team formation and project ideation. So we'll have a team formation event next week on Friday. Before that, you'll have some ideation slides, and we'll go over that beforehand. This is an opportunity for you to start thinking through what projects you want, what you're excited about, and then during the event, there'll be like pizza and that sort of stuff, but we will have people share their ideas so you guys can start forming teams and figuring out like ideas. Any logistics questions before we get started? Okay. So last time we were talking about interrupts, control registers. We'll do a little bit of review of this. Interrupt flow control, and then today we're going to talk about interrupt priorities and how to deal with concurrent and overlapping priorities. So a little review from last lecture. So interrupts are a method to asynchronously change program execution on the microcontroller. There's 2 types of interrupts. Essentially, there's system exceptions. We call these internal interrupts. These come from ARM itself in the sense that these are the things that you need for the core to actually function. Things like bus interrupts or memory misallocations or memory mishits or something. Those are all going to be system. And then there's event or external interrupts. And these are the things that you are intentionally programming typically. They're outside the core. The peripherals will be causing some code change to occur. And then we also talked about vector tables and stacking and unstacking, which we'll talk about briefly. So just a reminder, we have our core. Part of the core is this thing called the NVIC, the Nested Vector Interrupt Controller. This is a bunch of logic and state machine that controls interrupts. It takes signals from the peripherals, right? So these are literally wires coming from each of the peripherals that indicate that an interrupt is happening. And this thing knows which wire belongs to which peripheral. And then there's some control registers. So you're going to go, you don't write microcode or anything for this NVIC or actually normal code. Instead, you configure it with a bunch of registers, right? And then you're going to do that from the core. And so this will allow the core to be doing some execution. You'll set up some interrupts like, hey, when the GPIO pin goes high, do a task. This GPIO peripheral will cause this NVIC or this line to go high, the IRQ, causing the NVIC to take control away from the processor for a moment, give it another task to do, and then seamlessly put it back to its original state. So how does that happen? Come back. So you have some main program, right? Some external interrupt occurs. Well, you have to figure out, first the interrupt has to figure out which IRQ it is, and that's pretty easy because they're all mapped into it, but then it's got to go and relate the IRQ that caused this has to execute code at some location. And so there has to be a table or a structure or something that holds the address of what code should be executed. So the NVIC has what's called the interrupt vector table. This is stored in memory in the lowest location memory. First place in memory is the top of the stack, and then there's the resets. And so the NVIC will go into memory and it says, well, I know an IRQ corresponds to these particular locations in memory, and then it'll take this address and then start executing that subroutine. Oops. Should be some more builds here, guess not. Oh, I was building through this. Okay, so some interrupt comes, and then there's combinational logic. Essentially, it says the interrupt of nth index here corresponds to some interrupt over there, and then it's going to take, this represents memory space, this is address of memory space, and in here, held in memory is the address of the IRQ handler. Basically, it's just a fancy branch statement. Then you're going to go execute that code. And when you're done, you're going to return control back to main. And the goal is to make this as seamless as possible. So main doesn't ever know that anything happened here. There's just going to be a missing chunk of time. And how that's done is that there's the stacking and unstacking that occurs where the NVIC will take all the information that was required over here, so the lowest 4 registers plus PC and LR, the stack pointer, and put them on the stack. do this task, and then return all those variables back to the controller so that you're in main. Any questions? No questions. Okay. So we blasted through some of these slides before, but I wanted just to highlight the ones that are particularly important, and we'll go through some examples. So we have the interrupt enable. So these are a bunch of registers where you're going to go through, not necessarily configure the interrupts, configuring some of the ins and outs of the register are going to be done in the peripheral. But in the NVIC, you're going to go and write in and say, I want this thing enabled, or I want to clear it. So interrupts are inherently enabled or disabled. You have to, or they're always disabled. You have to enable them. And you might do that in your configuration, but you also may do it dynamically inside your program where you're saying, I want them to be turned on now versus a different time. So it's, whether it's initialization or in your program's kind of up to you. Then there's pending registers. Now these aren't necessarily things that you set, although it is possible, but these are more the registers that hold the state of the what's happening in the NVIC. And they're holding the bits of when IRQ comes in from the peripherals, it will show in a register. These are the ones that are pending. So it's a state holding device, really core to the function of the NVIC. And then there's another register that shows which interrupts are actually active. And then lastly, we haven't gotten to it yet, but we will today, there's another set of registers that tells for every one of these individual interrupts what's its priority. We'll talk about that in a minute. But the goal of this idea is that some interrupts are more important than the other ones. And so, you know, you're flying an airplane or something, a model airplane or something, and you have an interrupt for stability control versus, I don't know, directional heading or something. And some of those are more important than other ones, and you want the highest priority ones to always be executed first. And then we went through some of the details of these particular interrupts. One of the key takeaways is that you can have many interrupts. You can have, what was it, 256, I think? Yeah, 240, but it's up to, that's what ARM provides you. Hey, you could have this many, but your individual device manufacturer is going to have a subset because it's complicated to make an NVIC that has all these interrupts. And some of them are necessary, so you get 96 with your particular microcontroller plus the 16 from ARM. Okay. So any questions about the basic registers? Yeah.
What do the ARM interrupts look like? I know there's one that it's like the booting thing.
Yep.
What the other ones like be doing?
We could look through it. I don't remember them all off the top of my head. Let's see. I bet I have them written down in a weird way. So let's see. We have the reset handler, the non-maskable interrupt handler. Have no idea what that is. Hard fault, a memory management handler, bus faults. I'm not sure what the usage fault is, but these are the types of interrupts that can occur. Does that make sense?
Yeah, like if you're like accessing a memory that's not allowed, and there's like some handler for that.
Yeah. Basically, what will happen is, say your memory manager, which is a module that's we don't really talk about that much, but say that thing has gone to a wrong error or is starting to execute, is asked to go to a code space that doesn't exist, it will throw in a fault. And then it's this job's, the NVIC has, well, there will be a program that's written to handle that particular case. What happens when this fault occurs? Typically, for you guys, you're going to worry about the reset handler. That would be a thing that you want it to boot up in a certain state. Maybe I've certainly written programs where in a reset handler, you want to make sure the state of certain pins is known. So you don't want it to boot up and have the default state of LEDs. You want it to be a known state. Those sorts of things. Any other questions? Yep.
So where default states not known? It's default to a certain statement that you should go for.
So the manual will tell you what the default state of registers are. You might not like them, right? They might not help you execute your program. It could be you don't want to boot on your thing and then have your motor starting to turn. That would be annoying. And so you would go through and as soon as your thing boots up, the first thing it does is resets the direction of those pins, for instance. Now that's less of a worry on this particular microcontroller. I used MSP430s back in the day, which is a smaller microcontroller, to do really low power things, and some of those were random. You didn't know what bit state some of those registers were going to boot into. And so you better go and reset them to something known as soon as you wake up. Any other questions? All right. We went through, I'll hand out these worksheets again just so you go through. We missed one of the interrupts, or one of the slides. Let's give you guys a chance to do it. So if we look on the slide, we see that the top is interrupt request. So that's the IRQ signal that comes from the peripherals. So that's not a register state, that is just a signal, and there's going to be 96 of those. We're only showing one in these examples. Let's see, you need two more maybe. Now hold on, don't get lost yet. I promise I have interesting information for you. Hold on, just be quiet for a second, would you? Okay, I don't care. So pending status is literally, this is a register. This is a state holding register that's going to be caused when your NVIC reads the request interrupt IRQ. We'll have some other people send them back. If you guys could just send your sheets back in the rows to the people in the back, that'd be great. Garrett, could you just send these back? Thanks. You guys need more time to talk to each other.
So I sat in the back. I was like, no one can see me.
All right, so here we go. So we'll go through this example just so you guys can all remember. So we have some interrupt request. The interrupt request comes from the peripheral. It goes high. Then your NVIC is going to set pending status. This is a register, and it's going to go high. So between here and here, the NVIC did a task, okay? Then after some period of time, and this case is fairly quick, your NVIC is going to take your processor offline. Well, first your NVIC is going to say, okay, we're going to go into active state. So it's going to go from inactive to active, this particular interrupt. And so that's held in the active status register. And then the processor is going to go into handler mode, which is basically say it's going to do the IRQ. It's going to end it. When it ends, this is going to be deasserted. It's going to go back down. That's the normal state of how these things work. So do we have any questions on this? All right, in the last week, I'll just go through these. You guys can draw them out if you want, and we'll save it. We'll have one on the back that you haven't done yet. So in this particular case, we have our interrupt request came high, okay? And then our pending status went high as well, went into pending, that caused it to go into active, and then your handler goes. And the question happens, what happens when you exit your active state? Well, if pending's still high, what's going to happen is you're still going to exit, you're going to unstack, and then it's going to come back again. It's going to go from pending to still high. Therefore, we're going to go back into pending, then we're going to go into active, then we're going to go back into that interrupt. So in a sense, we kind of wasted some time. We'll talk about this wasted time here where we had to stack and unstack, and there's ways to mitigate that issue. All right. Any questions here? Yeah.
So when it re-enters, it only stays active. Oh, I guess, sorry, I looked at that backwards. So it flips off for a second and then just stays active and then just keeps looping since.
Yeah, in this particular case, because for whatever reason we don't know, but this interrupt request has stayed high.
Right.
Okay, and it should have come back down, but for whatever reason it says high, and so you can't go back into pending, or you went into pending here, you can't go back into pending when you're active. So it's not like it didn't immediately go back here because it was active. So when it became unactive, then it was allowed to become pending again. It became pending, then it went back to active. Yeah.
Why is it a less duration the second time?
These are magical, like Intel graphs, Apple graphs, where the axes don't matter. It's just giving you a feeling. There could be a variety of reasons why, say, you don't go immediately from pending into your active state. So maybe there's some variable here. Any other questions? Okay, so the next example was, what happens if you get multiple pending IR interrupt requests, right? So that line from the peripheral toggles 3 times, but here you've got the first one, you went into pending, but for a reason, who knows why the reason is, you haven't been able to get into active yet. What happens in that case? And so here, remember, this line is just is a register where each interrupt has one D flip-flop or one state holding device in it. So it's one hot encoding, so where each individual location denotes which register it is, and so there's not enough information to hold, hey, I got 3 pending interrupts. This only says I have a pending interrupt, then it went into active, then you went back. You don't do it 3 times, because there's no even way to hold that state information. What questions do we have with this? Yeah.
Different signals go a lot. The handler mode, is there a particular reason for that?
This just means Apple is trying to tell you that they have double X performance this year versus this performance. I have no idea. Like this, I just took these straight from the ARM Cortex, or the definitive guide from the ARM Cortex M manual. It's pretty good book. This is one of the 2 books I recommend. The first book was like a junior level or sophomore level book, a little bit more tutorial. It kind of assumes you didn't take 370. This book, the other book I recommend, assumes you've taken this course and worked in an industry for a year. And then you're like, aha, I understand everything in it. It's just a reference manual. All right, so the next question is, and this is the real question, should be on the back of your thing. What happens when I have an interrupt request, I've gone into pending, I'm active, and let me see if I can get the prompt correct. Request goes high, but then it goes high, well, the request goes high again in the middle of my active state. Is that correct? Do I believe that? Yeah. Solve that one, talk amongst yourself, and then we'll come back together. Is that correct?
This one, I think what
Go high.
which runs right at I was like, huh? This is like you're back in like a month.
Active signals. I think it's closing.
That's what I thought like here, like I have no clue.
It can't take so long.
What do you think is going to happen?
So I'm thinking like this goes into pending again.
Yeah.
It has to be different for the other examples, right?
No request.
We'll get it wrong, man.
I didn't feel like it's an incentive for me to
spilling an entire team off.
immediately and then high when pending is done, or active all the
Yeah,
way?
if once you're out of this, it will do declaration.
Yeah. I was kind of treating it as
A bash script. No warlock.
I don't think internet.
Need some time for that, but that's
That
about
would
right.
need. That would need.
I don't wanna write them down.
And
Let's go. Let's have a book interview for
You're not doing it?
we're giving false information, but
You're not gonna say shit down. I'm like, what are you talking about?
You can say that the state is changing there.
those there's diagonal. It just goes high and then
Say that active it's to engage you, so you do something.
The TikTok guy said he's like unique.
to talk to people who are
And I don't know. I guess I should write.
Just make it shorter. Here's what I can offer you. You haven't like done it.
are you taking like the MP or
And some of the techniques are whether you're in a position or
They're probably somewhere back there. Okay. All right, let's see. I see lots of good answers back there. There's probably one small point I'll point out that I didn't quite teach you correctly, which will make things hard. But here we go. All right, so the question here is, we came into interrupt, and we're in active mode. We're still active, but how did this thing get set again, right? How did just get interrupt pending again? Well, the thing I forgot to tell you, so you couldn't possibly get this answer correctly, but that this is, you can turn on pending if your positive edge triggered, right? I didn't tell you that, so you couldn't possibly know, but that's over here. Let's see, where's this example? This example, you didn't have a positive edge trigger, so it waited. Come back here. So then you had to get out of active for pending to go high again. That's just a level set, but if it's a positive edge trigger, then you can actually deassert pending again. The same thing happens on the end here, right? Oh, is this the right one? Yeah, this is the right one. So here, this ended, and then you had to go right back, and you were out of active for a moment and back in. It's just that pending somehow got set. How did pending get set? Because of the positive edge trigger. This rarely comes up. Yes?
The example for slide 55 where there's multiple pulses.
Yes. There's no state holding information there. It's already high. We never got out of pending. So pending was set here. Pending could have been set here, could have been set here. But pending never went low.
It kept overlapping from those people.
Yeah, before pending went, so in the example we're showing now, pending goes down early and you go into active, and then pending's reset. But pending never was taken out of pending. Pending was always asserted, so it just keep on being asserted over and over again. Okay. I got you on the trick question that you couldn't answer. Does anybody have any questions? How about in the back over there? Very quiet back. No questions? Yeah, fine. The brave question, yes.
Are the arrows supposed to indicate like it's positive or like negative edge triggered for the?
These arrows?
Yeah.
No, they're just telling you what actions happen. All right. So let's go on, talk about interrupt priorities. And this is how you know that one interrupt is more important than another interrupt. So the NVIC allow, you have a question?
So I'm assuming in the last example, so it went up without it's the positive edge trigger, and then it went down because the active status went down and went back up, right?
Yep.
Theoretically, like the previous active just kind of was just taking its time. Would it just also stay in that pending state, or would?
Yeah, it would have stayed in that pending state because it's pending until you come out of active. That's the thing that gets you out of pending is being inactive. All right, so the NVIC allows you to set the priorities of almost every interrupt. It doesn't allow you to set the priorities of ARM's lower 16 interrupts. That's not possible. They only use 5 on this particular chip. But those are reserved. You can't change those, but you can say that change the priorities over everything else. Here, importance interrupts can be preempted by lower importance interrupt, and we're going to use the term importance because we're actually going to use Gulf scores for interrupts. We'll talk where low numbers mean it has higher importance. But basically, if you have a higher important interrupt, you want it to preempt or interrupt another interrupt. Here we're going to use Gulf scores, so a lower number means higher importance. So there's about a bunch of three fixed priority levels, and then you have up to 256, but in our world, you have 256 programmable priorities. And there's particular registers for that. They have addresses, and then you're going to go through and say, okay, this is how I have 8 bits I want to use to represent the priority number for a particular interrupt. All right, so it's inverse relationship. Lower priority values mean higher urgency. So if A is 5, then A is a lower priority than B, so B has higher importance. We'll try to make sure we talk about it that way. And then these are the most important interrupts. So reset has to be more important than a hard fault because reset is like the thing is coming on, right? Nothing can interrupt that. And you might think like, doesn't that happen immediately? Well, it's not a light bulb. There's actually a lot of boot up sequence that has to occur for the processor to actually land in main and be executing your code. So this is the most important one. And so we use a register structure to keep track of this. So here we're going to have, we say there's these 8 bits of potentially up to 8 bits to denote the priority of a particular interrupt. And so we can chop up these bits in 2 different ways with 2 different numbers. So there's the preemption priority and the sub-priority. So preemption means of 2 interrupts with different interrupt priorities, one is going to preempt the other one. So the lower the priority number or the more important is going to preempt. But then you may have multiple interrupts of the same preemption priority. And then you use the sub-priority numbers to say, well, this is the ordering of how those interrupts should occur. So there's like, the big priorities, and then once you're already interrupt, how would you sort, essentially, the interrupts that are still pending of the same value? We'll walk through a bunch of those examples. There is a small quirk for this particular device, and that is that it does not even implement the lowest 4 bits of the preemption priority register. Just because having that many choices actually isn't that useful. So you can write to these, but they'll do nothing, and they only give you the top 4 bits. And you get to manipulate the top 4 bits to have more or less preemption or sub-priority. So you can reallocate, this is what this table is showing. You can reallocate the number of bits, and there's a register for that where you can say, well, I want maybe 3 bits of preemption priority and only 1 bit of sub-priority, or I want 1 bit of preemption priority, and then everything else is a sub-priority. So that gives you some flexibility in controlling which interrupts interrupt other interrupts. Yeah?
Why do they split it out into preemption priority and sub-priority? Couldn't they just treat that as one number and have it achieve the same purpose?
Yeah, but you run out of space pretty quick. That means I think that's more interrupts or that's not enough to represent all the interrupts that could possibly exist, right? Not enough bits. And so they're basically saying the best strategy is we'll have 2 bits, or say whatever number of bits of things that have different priority, and then we're going to sort the rest of the bits, pendings. And this is really about which pending thing should go next. Yeah.
What does preemption versus sub mean again?
Preemption priority is I have 3 interrupts, let's say, and they all go off at the same time. Or while I'm in an interrupt, these other 2 interrupts go off. Should this one that just went off interrupt the currently active interrupt? It could. You'd want that if you had like a hard reset, right, or a bus fault or something important. Then it says, all right, I'm interrupt. I'm not going to interrupt this interrupt, let's say. It's just too important. The other ones, I see some things that are pending, but they're not particularly important enough. But when I leave this interrupt, which one of those pending interrupts should I do first? And that's what sub-priority is. Yeah.
They're not using the 4 bytes, the 4 least gigabytes. When I just make like a 4-bit priority versus an 8-bit.
Why would you choose this?
I used the whole 5 and
So ARM says you have to use 4. Or sorry, ARM says you have to have 8 bits, okay? But STM said, look, that's too many. My NVIC will be too crazy. It'd be too hard to implement. It's not worthwhile because I only have 96 interrupts. So I'm only going to do 4, right? Why? I can ask you. Why don't you take 30 seconds to ask each other or discuss why has STM said I'm only going to do the highest bits here and not just use the lowest bits? Why would STM make that decision? Talk amongst yourselves.
Just
Yeah, I was going to ask the same question. I have not
By the way,
You're right.
If you have 2 bits,
It's just
all right, what do we think? Why not just use the lowest 4 bits? Why actually use the highest 4 bits and just leave these unused? Why would you make this architectural choice? There's got to be somebody who has a guess. What happens if you are trying to manage a set of code across multiple processors? No? So, as long as your preemption and subpriority are about the same across different processors, well, this actually doesn't even matter. Here, say you transfer your code to another processor that has the lowest bits. These interrupts will still work, right? And these are just more fine-grained control over those bits. I think that's the reason why they're doing it. Okay. Because interrupt priorities are so important, they actually have a key that you have to write into a register if you're going to change the allocation of your preemption priorities. So what you do is you have to take, it's not like a private key, it's not like a security thing, but there's just some value, and then you have to write it into that register and that unlocks it so then you can change your priority groups. And that's just because they want to make sure that no code error occurs that's going to drastically change the execution of your device. You have to intentionally do this. So in lab, you'll have to look for this particular code to change those preemption priorities and those group priorities. All right. So let's go through an example here. So say we have the external I/O lines here. You can go offset. They have this base offset for the interrupts from ARM. And say we want to go give it some value. Okay? And so that really is, there's this data structure here, a memory structure that lays out different interrupts. And then there's 4 bits here that you're going to go place into there. And it's got to be the upper 4 bits for this particular application. So you're going to set it in there, and that will set the interruption priority. You can actually do this in assembly if you got real excited. They actually have a specific instruction for, these are for masks, sorry. You can go and change your execution masks. So you can go and change which priorities should be executed. So you could say anything that's less important, it has to be more important than this value, then you should be able to execute it. And so you have some instructions. You actually have assembly instructions, of course, you can do it in C as well, where you can change the value of the priority mask. And you can set it to, you can set them all on, you can set them off, or you can set it to a particular value. There's also a fault mask and the base priority mask. All right, so let's talk about, I think interrupts make more sense when you bring it all together and you look at overlapping interrupts. So let's talk about this case. We have your program stack. We have, this is execution time. This is the difference between, we'll say software. They call it hardware sometimes, but this is basically in your interrupt handler. we have registers here that represent your priority table. So these are 5 different interrupts of different values. Then we have holding the state of if it's pending or not is a pending register. All these interrupts are active, so you have another register for that. So this is your enable register. And then you have, or sorry, this is which ones are enabled, and then these are the ones that are active. So right now, we have nothing's active, they're all enabled, nothing's pending, here are our priorities, and here's our base priority, basically saying that any value smaller than this can be interrupted. But you could decrease this value, say if you put it to 9, and even if this thing is enabled and it's in pending, it won't get processed because your base priority is smaller than that particular value. Yeah.
Is that saying that priority table, is that saying that the interrupt that's in spot 3, since it has the lowest priority of 3, that would go first?
Yes. Yep. Or stated another way, if it's active, nothing else is going to interrupt it. Yeah.
Is this sub-priority or preemption priority?
This is all preemption priority right now. We'll talk about that particular case in a little bit. Yeah.
Since here's like 256 versus saying like we're gonna allow all possible interrupts.
Yeah, this is just saying this is the base priority. You have to have a priority larger than this. Or smaller than this, sorry. Something that's more important but smaller than this. And you can change this number if you want to, I don't know, your important part of the code you don't want to be interrupted. You can disable the interrupts just by, or disable low priority interrupts just by changing this number rather than going to each individual interrupt and changing it through multiple instructions. Yeah.
Is there like a function call that disables all interrupts, or would you just do that by just lowering base priority all the way down?
There is a function for that, but one of the easier ones is just to do base priority. It gives you more control. Yeah.
Does this say the priority number, or does that say that coding?
I'm sorry?
Can we control like the priority number?
Yes. So that is in the preemption priority bits that were over here. This is essentially the table. You have a table and you can go put your bits into here. And what are those bits? Those bits are these bits here. And right now we're talking about the preemption priority. We're not talking about sub-priority. So you're setting these values. So this is, you can set the allocation, but you can actually set what value these are. Okay. All right, so let's say an IRQ4 goes off. Okay, so that's going to cause us to start stacking. And here's our program stat. So we have PC, the program status register, the link register, R0 through R3 and R12. You put those on the stack. That has caused us to be in pending. Right now, because we're in the process of stacking, we're not active yet. It's going to take 6 cycles or so for us to get into pending, or sorry, for us to completely stack and get into our active state. Then we're going to go into our IRQ. So here's the idea here is that hardware is causing this to happen. This is a program that you've written. This is another program you've written in your interrupt service routine. It's just that stacking or the hardware got you there. It wasn't a function call that got you there. And so now we're in that interrupt. We're not pending anymore, so this register has been deasserted, but we're in the active state. Okay? And we've set our base priority to 6, which means that 10 or 8, if they happen right now, they cannot interrupt this. It will keep going. They will just stay in pending. But if 2 or 3 happen, then they would interrupt this particular interrupt. And then you're going to branch to link register. Remember, this is that special link register. That's the value that's like FFFF6 or something, and that's going to tell the hardware. You're going to link to a location that tells the hardware, okay, it's your job to unstack. You're going to be out of active. You're going to unstack, and you're going to go back to your normal program execution. That's the normal way a single interrupt will occur. What questions do you have? Yes?
What does
You have to be really loud.
What does enable do?
Enable just says that I want this particular one of these interrupts to be enabled and on. So I could make this, if I had made interrupt 4, if I had made, let's see, this bit 0, this bit 0, then if the interrupt comes, it doesn't do anything. Okay? She says, no, I don't. She says, no, that's bullshit. I don't like any of that. Okay, so you could go through and tell your peripheral, hey, I want you an interrupt pin. When I see a rising edge on this pin, I want you to go high and send the IRQ to the core, okay, to the NVIC. But the NVIC does not have to listen to you. Listen to that interrupt, or that interrupt request. Instead, it could say, put a 0 here, and then it will ignore interrupt requests from line 4. Does that feel good?
So would that be something that happens at the very beginning, like when the request, there's a request, or would that just be at the beginning when you, let's say, turn on something and it's like through?
Enabling is done by, I didn't quite hear everything, so my apologies, but enabling an interrupt happens by you as the programmer. You're going to set these things to be enabled or disabled. So not all interrupts are on by default. And so you can go turn them on. And you can turn them on when you kind of reset the entire device as part of your boot up routine, initialization routine, or you can set them dynamically in your code. Say, okay, now turn on for this particular function, then turn off later on. Does that answer your question? Okay, great. All right, so let's look at when things get weird. So things get weird when we have nested interrupts, and that's the name of the NVIC is a nested vector interrupt controller, because the idea is that multiple interrupts will be happening on top of each other. And so the goal is that higher interrupts occur, lower importance interrupts will not interrupt the interrupt, but higher important ones will. And so we'll walk through this example here. So here, we're kind of back to where we were before. So we're in a program, an interrupt 4 occurred, we started stacking, and then we started doing this task here. Actually, this shouldn't be here quite yet, but we started doing this task. And while we're doing that task, an interrupt occurred. Okay, so interrupt 3. And so now, interrupt 3 has a priority of 3, which is lower than the base priority. Therefore, we're going to have an interrupt, interrupt, and interrupt. And so when that happens, we go to pending. And oh, sorry, this was maybe IRQ was just using the stack. This is what we're demonstrating here. So if we go back, back. So here, I don't know what the IRQ was doing, but it had some data on the stack, whatever its function was, I don't know. And then it gets interrupted, so now we're gonna do stacking again. So now we've gone into pending, this thing was enabled, this one is still active, right? 4 is still active, but 3 is taking over, and now we're gonna stack the state of the register that was responding here. This entire thing is being stacked up here, the state, and now we're going to start executing IRQ3. So IRQ3 was pending, now it's active. Now we have 2 things active, okay? IRQ3 is active, we execute that, we get to the end, we branch back to that special location, it unstacks the data that was held here and puts that back in the data necessary to execute this, puts that back in the core, and now it goes back to this particular that one's pending, or sorry, that one is goes to active. We finish executing this, and then we unstack and go all the way back to our main program. What do we think? Yeah.
If you were in some interrupt, and then there were like 2 nested interrupts that happened, so there were basically like 3 active bits.
Yep.
How would it know which of the other active bits to go back to after it?
Well, let's look at this exiting strategy here, right? It doesn't actually keep track of what was pending beforehand. That information, like there's not an extra register for that. It's held here on the It's held here on the stack. This is the state holding device. So it says, when it exits here, it says BXLR, right? And then it unstacks all this data, puts it back in the core. That just happens to be, you're in this IRQ. You're in this interrupt. Does that make sense? See, ask your question again.
I guess maybe a way to rephrase it is like, what is the piece of data that's indicating which active is corresponding to your current interrupt?
Nothing. The way that information is held is through the act of stacking and unstacking. Okay? So it's kind of the sequential action of I stack this, therefore that's my last one, and then I stack this again, so the stuff that's in the stack is what's needed for this. So when I unstack, I'm going to do this, right? And so there's this unending chain of on your stack is all the interrupts that you're in, and it's just sequentially going back through them. Yep.
What is each level in the problem?
What's that?
What is each level? Yeah.
Each level here. So this is the importance. The lower the number, the more important it is. So in this particular case, we started out in 4, which had a priority of 6. This is the interruption or preemption priority, not sub-priority. Okay, I'm at 6. And therefore, if 1 or 0 came in, it could not interrupt because these values are larger. Okay, but 3 came in and 3 was able to interrupt.
And then what is like the 4 or 3 means? Is that connected to a pin or something?
These? Yeah, these are essentially these signals that come from to the NVIC. And so number 4 corresponds to this particular interrupt priority. So if you look in the vector table, those lines correspond to those particular interrupts, and each interrupt has registers associated with it, which is pending, enable, and active. And so the NVIC's keeping track of how they're all coordinated together. Yep.
What is the base priority change?
So the base priority changes. It was at 256 before this happened, and now it's 6 because now we're saying I don't want to be interrupted by anything less important than me. And so these are less important. And therefore, it does some logic when this IRQ comes in, we're going to do some logic to say, well, you're asking for this for interrupt 3. It happens to have a level of 3, which is less than 6. So now I'm able to interrupt. So this is keeping track of the state here. Yep.
Hardware adjusting the base priority, or like am I gonna
hardware?
Hardware.
Yeah, I mean you can change the base priority if in software you know I'm coming to a really critical section of software. This actually often happens when you're pulling in, you're decoding serial data and you don't have any peripheral serial. We call it bit banging, where you're taking in, you're checking if it's high or low. You don't want anything to interrupt that task because you'll miss some data edges. So that is a time when you might change your priority level manually so that nothing can interrupt you.
So is this like some sort of split flop where when you allow some sort of interrupt, it's like enabling it to read in the priority value into the base?
Yeah, it's just some combinational logic. It says whatever's in this register, is it greater than this other thing in this other register? If it is, then do a thing.
I get like the comparing like to when something can go interrupt the interrupt. I was saying like what's actually when is it adjusting the value of the base?
When you start, so we're going to watch right now. I'm going to advance forward. We're going to stack here. And then the base priority changed when I entered that one. So there's some combinational logic that says when I'm in an active IRQ, then I'm going to change the base priority to that. What other questions? Yeah?
I'm trying to understand what happens when you exit. So you change the base priority back to what it was.
Correct. You don't even have to look for active bits. All you do, so I'm going to go from IRQ3 and I'm going to go back to IRQ1. What is the function? What's the mechanism that does that? Well, let's just say whatever. This is just the data that the IRQ is using, so ignore that for now. Assume that the IRQ is responsible enough to pop off its own data. Okay? And then the action of unstacking, just the mere action of unstacking, forces this data to now go back onto the core. So mechanically, like a hardware function will take the program status register, which encodes this information, the link register, R0 through R3 and R12, puts that back on the register, and then changes PC. PC is going to push back to this location right here where it got left off. So that's the mechanism for.
So unstacking does everything the PC.
Yep, unstacking does everything required to put us back into IRQ4. And that way, there's no state holding device other than the stack that knows or has any record of how many interrupts deep you are. You could be 20 interrupts deep or something, right? And the only place that information is held is on the stack. Yep.
Does an interrupt of the same priority of another interrupt that interrupt?
No, it has to be a higher interrupt. And we'll go through tail chaining, which will answer, I think, the next question you have. So tail chaining is what happens with something of the same or lower interrupts an interrupt, okay? Kind of the opposite question you asked. So here we go. We're in IRQ 4, and then a new interrupt's going to come. What interrupt is it going to be? It's going to be IRQ 1, which has a lower interrupt, lower priority. So we're not going to preempt. Instead, and we're not going to unstack. Now the reason is, so if I went unstacked, I'd go all the way back to main, and I'd waste a bunch of time in the action of unstacking because there's a bunch of memory writes. We have to take reads and writes. We have to take stuff out of memory and put it in the PC. So instead of unstacking, we're just going to wait for a second. We're going to do some other. So we're going to get everything set up. We're going to switch to a new IRQ here, but all the original state that holds program is just going to stay on the stack. And then we're going to go, when we're done with that, we're going to unstack and go back to program. So here we're saving ourselves, actually, I'll have to look it up. I think this might be 12 cycles, and this is shorter. This is like 6 or 3 cycles or something. I forget exactly. But basically, you save the action of going all the way back to the program. You just wait and then go directly into your IRQ. So that's if the priority is lower. Yes?
That waiting period, what's all happening? Is it just setting PC?
Yeah, setting PC is probably got to update the base priority sort of things. Yeah. But it doesn't have to change. You don't have to hold the state of the microcontroller, right? You don't have to update that. You can just leave it on the stack.
What is like the same preemptive priority compared to like a, let's just say like a lower sub?
So
what will come after?
So I think we have an example of that next. No, we have late arrivals next. So the question is, this was a lower priority, so it waited here. When does sub priority come in? Imagine if I had a number of interrupts that came in all at level 10. So now maybe 1, 2, 3, 4 interrupts are all pending. We see them pending, and they're all level 10. How do you determine which one of those 10 goes first? Well, the sub priority bits, we're not really showing here. We'd have to have another register channel here. Would indicate which one should go first. Okay.
What you're saying is you check your preemptive register first,
Yep.
then you check your
Sub priority.
if you have it like a tie.
Yes, and that tie will only exist for pending things. All right, and then we have another one called late arrivals. So what happens when an interrupt, while you're stacking, if another interrupt of lower priority number or higher importance happens? So here we have a case where we're in a program. We got interrupt 4, and then while we're stacking, we got interrupt 3. So what you wouldn't want to do is like double stack, like stack this, then start 4, and then immediately have to stack it. That wouldn't be effective. So you don't want to do this. It doesn't really make sense to do that because you're not even really in, nothing happened in 4 yet for needing to stack. So all you do is you just change the priority at the last minute, or you just change which interrupt is going to be there. So you go and take, at the very end, you're going to go look at pending, and well, let's see, what are you going to do? You're going to figure out that this one has a higher priority, and more important is lower priority number, and then you're going to execute that one instead of 4. So that saves you some cycles. Go to 3, and then because 4 was lower priority number, or sorry, higher priority number, then you're going to do tail chaining here where you're not going to unstack all the way. You're going to go immediately that one, then unstack and go forward. So basically, you have up until the last cycle for an interrupt to come in, and you choose the more important cycle or interrupt. Yeah.
Stacking is completely hardware, so it just won't be. There's nothing like, I guess, nothing can happen in between it.
Correct.
Okay.
Yeah. There's no stacking inside of stacking or something. It's not allowed.
Is it like atomic?
Yeah.
Okay.
What questions do you have about interrupts? Have one more example to go through. Yeah.
How do you know which active bit is with on?
Like which one is, like what the bits correspond to?
Yeah.
So we, like way back here. There are registers for that is the short answer. So there's, oh, you guys can't see that. There you go. So there's an active register. It's in this particular one, what is it? 1 bit for each interrupt, and then there's n 32-bit registers up to the 96 that you have. And so, you know, here's interrupt 0. There's a bit, it's read only, right? You can't write to it, and it will hold the state of whether that one's active or not. So there's a register for that.
Okay. Will that get pushed to the stack on the interrupt? Is that part of the stack?
No, it doesn't need to get pushed because this doesn't actually hold real state information that you would need, like if you're stacking and unstacking, because that's held on the stack.
Right, but the kind of like the knowing which active to go back to if you're going in like deeply nested interrupts, like which I was asking before.
But remember, where is that held? What's the structure that holds that information?
Well, I kind of thought it would be that register,
nope.
But maybe not.
Nope, it is, literally is the stack. So after I leave IRQ3 and I unstack IRQ3, which IRQ am I going to next? By definition, right? Because the action of unstacking will instantiate the information required to do IRQ4 on the processor. Right? This information is going on the processor. You're jumping back into it. There's no other method to make that decision because you BXLR'd, that's it. That's the only thing that can happen.
So that's like hardware deciding that, or like hardware knowing that.
Well, the hardware is dumb. As dumb as hardware can be. It says, I get a BXLR to FFFF6. I take what's ever in the stack, I put it in the core. It just happens to be that that information in the stack represented the action of doing IRQ4. And now you're back into IRQ4, and you're going to do it. So the action of the method is unstacking puts you back to where you were. You keep unstacking, unstacking, unstacking with a BXLR to FFF4, so until you're back into main. How's that feel? Okay.
So what about this case? So you have, so you're on level 4.
Okay.
And then you interrupt that guy to go to level 3.
Yep.
And then while you're in level 3,
yep,
a new interrupt comes in that's lower than 4 and 3, so maybe it's 5.
Okay.
Would it unstack to 4?
Wait, so it's
to do that?
the priority here is 5, which means
Yes.
Okay.
A new interrupt that comes in while you're in 3.
so it won't do anything, right? Because it's not.
Yes.
Because it won't interrupt. An interrupt doesn't have enough priority. So then you would just execute. You go to 3. You'd go unstack. Let's see what it will do. It'll unstack. No, you get to end of 3 and it'll figure out what it should do. It should figure out if it'll look through pending, I guess, and say, is there anything higher than 4? Any interrupt that's more important than 4? In this case, there won't be, right? Because it's 5. No, it would. Yeah, wait, no, it's 5. Right. Then it would do 5. Then it would go back to 6.
So you know, jump to 5.
Yeah, say you're. So let's say this. Let's say it was 4, and while you're in 3, IRQ 2 comes in, which has a 5 priority, right? Then instead of going back to 4, it's going to do late arrivals or tail chaining. It'll do tail chaining, right? Where it'll say, okay, I'm just going to jump to 2 here because it's more important than 4. It's going to do this task.
Sorry. The example I meant to say was like it's a lower priority than both.
Of. So we'll change this one to literally 2 or something. Then it'll just interrupt the interrupt.
Oh no, I meant a priority higher. Okay, I meant a priority like it's a lower.
We use the word importance.
It's less important than both.
Like
an
8.
Yeah, 5. Okay, it's less important than no. Then it's going to go. Then it'll go back to 4. Then it'll do 8 at the very end.
Okay.
Because the base priority will prevent it from happening.
Oh.
So this go unstack 3. finish 4 and then do that
Yep.
lower importance.
I was wondering why wouldn't it like tail chain to that current thing?
Why won't it tail? Well, that's because it's base priority. Why won't it tail chain to this, right?
Yeah.
After 3?
Yeah.
And your statement is, how does it know 4 exists?
Yes, because it's on the stack. That's what I was thinking. It was like it's on the
Well,
stack.
we know what's active, and so you could go through. I guess I have to read the manual again, but it should know in that particular case that it should go to 4. I know it will go to 4 rather than going. It will always do. It'll do the interrupts in order of priority. So I have to think through the mechanism, like what's the actual logical mechanism here. But it's going to look at active to see what it should be doing next.
Oh, right. And so it knows to tail chain when it's in pending and not in active.
Yeah.
Oh, okay, gotcha. That makes sense. Yeah.
Yep.
The thing is only high during the stack, right? It never goes back high even when it's being interrupted by the next one.
Pending goes high when you're not in active. So you could be, so say I got IRQ 10 here, or this one. I have to do all this sort of stuff. It's going to be pending until I get to it. So it's not just stacking. It's when it hasn't been serviced, basically.
When it's being interrupted by another interrupt, it doesn't go back to pending.
Well, to be interrupted by an interrupter, you must have been active. And so when you're active, you transitioned out of pending into active. So yeah, that curse can't exist.
I'm not 100% sure if I understood what you were just saying. So let's say you had IRQ 2, which has a priority of 5.
Yep.
So were you saying that after you were done with IRQ 4, it would
Correct.
tail chain that?
Yep.
But IRQ 4 has a priority of 6. So wouldn't.
Okay, sorry. That's probably where I got confused him. It will do the interrupts in the order of the priority. That's the goal. So if I misspoke, sorry. Yeah. So if it was 10, for instance, it will do 4 and 3 and then do 10 at the very end.
Okay, so in this instance, though, it would finish 3 and then do 2 and then finish 4.
Yes.
Okay.
Yes. Okay. Have I confused everyone enough? Fantastic. Let's move on to the next problem. Confuse you in a different way. Yeah. It's just to remind you, these are review slides, depending where we got, but just to remind you, literally, there are wires that go back to the NVIC controller. Those are the interrupt signals. There's multiple of them. Okay. So here's a slightly different example, just so you can see it in a different way. So we have the interrupt numbers. So these are, so the interrupt numbers. So these are in kind of interrupt table. These are their locations. You have which ones are enabled, you have which ones are active, you have which ones are pending, and which ones in their priority. So here we only have one thing enabled, okay? And then we have program, we have our stack, and their stack's over there, and here's memory, okay? And so let's see. So we have that IRQ for external interrupt 3 goes off, which then we would go into this thing here, figure out what, into our vector table to figure out where should IRQ3 handler be. What's the address of this particular thing? Okay. Oh, sorry, that's where the code is. The address is somewhere in here at the lower bits. Then what happens? Then we do stacking. Why the arrow points that way, I don't know. That looks like a slide mistake. And so then now we've set this to pending. It's still enabled, and that's what the priority is. So nothing's going to interrupt it. We're going to load the stack up. That's what the pending process does. We're going to be in IRQ9. We're going to BXLR to FFFF6. And then we're going to unstack. And then we're going to go back to where we were in the program. I guess that's just, usually this helps if we do it the next day, but anybody have any questions with that?
where is the ISR 9? Oh, it's here.
You guys say that again.
Where is the ISR 9? It's like the 9.
Yeah, that's a 9. That's just the interrupt number in this example. All right. So here we'll talk about a different version of preemption. So here we have stacking. So now we have both. So again, these are registers that are in the NVIC that you're going to write to set up. At least, I mean, you're not going to write to these. You're going to write to enable. You're not going to write to active. You're not going to write to pending. But you can write to enable that's in the NVIC. And you say you've enabled these two interrupts. And interrupt 3 comes in. And that happens to be ISR 9. This is just the location. This is just like the external interrupt number 3. 9, and then DMA channel comes in. So what is a DMA channel? DMA is direct memory access. We'll talk about at the end of the course. Basically allows, if there's another controller on your device, it doesn't have all the functionality of your core, but it allows you to program it by writing to its registers. It will do memory transfers for you. So for instance, you can go into your ADC, and every time the ADC peripheral goes off, which allows you to measure things on the external world, like analog voltages, and you can go put it into memory. Or say you had a serial bus. Instead of wasting the core's time to do this, you just tell the DMA to move that data around for you. So it's an extra functional module for you. Anyways, so let's just say that goes off. And now let's see, what was the priority? So in this example, this is 5, this is 3, so 3 is more important, so you're going to interrupt your interrupt. You're going to do stacking. So here's the original program, and then here is the state of ISR 9 put on there. Let's see what happened. Now they're both active. Okay. You're going to execute ISR 12. Sorry. And you're done. You're going to unstack that. You're going to go back to 9. It's become unactive. Nothing is pending. And then you're going to unstack that program there. Any questions? Yeah?
So the other channel is not enabled, like would you not even, would it be possible to send signals, or you could send signals and just wouldn't interrupt anything?
So you could say you got whatever this is, IRQ 11 here. Here, because it's not enabled, it doesn't matter. So those IRQ can come into the NVIC. All they want, it'll just be ignored. And so like when would that happen? That'll happen if you say you've configured a whole bunch of interrupts on your device and you've told the peripheral, hey, when this event occurs, I want you to raise this IRQ pin, because that comes from the peripheral. It's not the NVIC that will set up the IRQ pin going higher or signal going high or low. But the NVIC has a choice of listening to it or not. I did put cycle counts on here. So tail chaining, this is 6 cycles. I think it's 12 cycles to get into here. Yep. No, it's 12 cycles for stacking and unstacking. So this is why you don't want to do tail chaining, or this is why you don't want to stack and unstack, because now you got to wait 24 cycles. But tail chaining only costs you 6 to go from one interrupt to the next interrupt. So that saves you time. All right, we blasted through interrupts. 10 minutes fast. What other questions do you have? Yeah.
I don't think there's enough interrupts for this to happen, but could like Stack Overflow happen if you have like a crap ton of interrupts happening with like bad priority numbers, like just one after another and after?
Probably that, plus like you using the stack for your own things. Yeah, you could probably Stack Overflow. Any other questions? All right. Well, on Wednesday we'll talk about timers then. Great.